Okay, at this stage in our study of integration, we come to the technique of partial fractions. If we have a long line of situations that we've dealt with so far in dealing with integration, and there's one type that we're going to come across here that none of our techniques are going to work. If we try to use U substitution, it will not work. The integration by parts will not work. That's generally going to be used for multiplications, as we know. What it boils down to is if we come up with a function like, say, x minus 13, and we have 2x squared minus 7x plus 3 on the bottom, okay, a function that is a rational function, then the technique of partial fractions might work and help us integrate this. So ultimately, if our job is to find the antiderivative of said function, our first choice here would be to try to use substitution here. So if we let our u be 2x squared minus 7x plus 3, our du then would equal 4x minus 7. Now here's the problem. With our 4x minus 7 and our x minus 13, there is no constant multiple that we can multiply this by or divide it by, if you will, to get x minus 13. It's just simply not going to work. The only way we can get x to be 4 is multiplying by a quarter, and if we multiply this by a quarter, we certainly wouldn't get 13. So therein lies the problem. U substitution is not going to work in this situation. So what it boils down to is we have another technique to deal with rational functions like this, and that's called partial fractions. So the technique is going to work as follows, and it's somewhat of a specific technique, because really it's only going to work if we can factor the denominator of this fraction. So we'll start with that. We'll factor the bottom of that fraction, and we'll rewrite this sentence as 2x and x. And then we need to build a 7 here, so we'd have a 3 here and a 1 here, both minuses, of course, with the factoring that we have. And then now our sentence reads x minus 13 on top, and these two as the denominator. So we haven't changed anything except for we've just put the bottom in factored form. Now, what it boils down to is that what would be convenient for us is if we could take this and we could decompose it into the terms that it came from in terms of two rational functions that we could add together and get this. Okay. Now, what it boils down to is that whatever the two factors we get, we're going to take and write those as an addition to one another, and we're just going to put two numbers on top, a and b. Okay, and these a and b could represent numbers or expressions. Okay, so bottom line here is we want to know if we were to add these two fractions together, this one having this denominator and this one having this one, okay, what would the a and b have to be in order to give us the result that we see from here? So we're basically unadding two fractions together is what it boils down to. And we can see that if we were to add these two together, they would not add right now because they don't have a common denominator. And hence the common denominator would be the 2 multiplied, which we see here. Now, so getting back to that now, like I said, if we were to add these together, we would need a common denominator. So that means that the common denominator would be the multiplication of these two, and therefore a would have to get multiplied by the other denominator, which is x minus 3. And b would have to get multiplied by the other denominator on the left side, which would be the 2x minus 1. So this would ultimately be our numerator for the fraction if we were to add these two together. Okay. Now what we want to have happen is we want that numerator to equal x minus 13. Okay. So the question is, how in the world do we get that to happen? Well, bottom line is we need to write a system of equations here that we can solve for a and b. So let's see how that works. So we're first going to go ax minus 3a if we distribute here. And then we're going to go 2bx minus b here equals x minus 13. Okay. And then what we're going to do is we're going to collect the terms that have x in them, ax and 2bx, and then minus 3a and minus b here. And we're going to factor out an x, and we're going to have a plus 2b here. And then we're going to factor out a negative 1 and have 3a plus 1 here, plus b I should say, here. Alright, now ultimately we've got it down to where we are at the point where we can write a system in a and b now. Because ultimately we have a polynomial on the right and a polynomial on the left. We have something times x here minus something, and we have something times x minus something. And if these two were to be equal to each other, that a plus 2b quantity would have to equal 1, because it's essentially the coefficient on x on the left is equal to the coefficient on the x on the right. So this being a plus 2b and this being 1 would mean our a plus 2b would have to equal 1. Okay, and then also we can see that again, in order for the left side and the right side to be equal, this quantity in parentheses 3a plus b would have to equal, guess what? Well, 13. Okay. And why is it positive 13? Because we already have a minus sign here, we just equate the two numerical parts and we have a true sentence. So with that said, now we have a system of equations in A and B here, and if we want to solve them, we can use either elimination or substitution. I would use substitution if it were me. I'd multiply this one by 2 and then add those together. So we'd have A plus negative 6A, that would be negative 5A. These two would be gone, because that's the purpose of multiplying by negative 2. And then if I multiplied this one by 2, I'd have negative 26 plus 1, that'd be negative 25. And conveniently in our case, this works out to be A equals 5. And of course we can substitute now the A into one of these two equations, and if we substitute it into, let's say, this one, we'd have 5 here. If we subtracted, we'd have 1 minus 5, negative 4. And so ultimately B would be 2 into negative 4, which would be negative 2. Okay. So now at this point, what we've done is we've found the two values that we should have on top of the two original fractions here in order to get two fractions that we add together, and they would give us the original result, which is x minus 13 on top. So taking a look a little bit further, keep this here, we have our new integral now reads 5 over 2x minus 1 plus negative 2 over x minus 3. Okay? So that is our new integral at this point. And my challenge to you at this point is if you may believe or don't believe, you can choose whether to believe or not, whether this system works or not. But bottom line is, we could check this because we could get a common denominator with these two and change the numerators appropriately and add them together, and guess what we're going to get? We're going to get x minus 13. So you can try that on your own if you'd like to make sure that checks out. But bottom line here is, once we have it like that, now we can write an integral of 5, 2x minus 1 dx plus, and actually we can write it as minus, but we'll still take out negative 2 here. And then we'll have 1 over, actually, let me change that. I'll do one step at a time. Let's skip a step, so do the negative 2 out in a minute. So we can ultimately separate those two because we know that the integral is a linear operator, which means we can separate sums, and we can also factor out common or constant multiples, and so therefore we'd have the following integrals. And the reason that works for us nicely is because now these are just ultimately natural logs. Okay, and this one we have to be careful with a little bit because we have a chain rule issue with the 2x here. We know that if we let u equal 2x minus 1, our du would be 2 dx, which means that we'd have a half du to replace here. So ultimately we'd have a half, so we'd have 5 halves out in front, and then we'd have the natural log of 2x minus 1 here. And then if we do the other one, we'd have natural log of the absolute value of x minus 3 here, and we'd have plus c here. And in this particular case, we'd be done, because we've integrated both parts, and we've come up with an answer that is correct. And once again, if you so choose, you could theoretically differentiate both of those and see if you get back to that same argument that we started with when we anti-differentiated. Okay, so but bottom line, that is that's essentially an overview of how the system works. We're going to see a couple other variations here in just a moment. We're going to look at another one that works similarly to it, and that's going to be the following. We're going to do 2x plus 16 over x squared plus 6, or x minus 6, that is. So we're going to integrate that, and this happens to be number 6 from your book, your homework assignment. And if we follow the same procedure, so you can see it again, we're going to factor the bottom. So this is the order of the techniques that we're going to use. We get x and x, we get plus 3 and minus 2. And we're going to separate the two bottoms into two separate fractions, having an a on top and a b on the bottom, or a on top of the first one and b on top of the second one. So that's going to be our first two steps. Then from there, we're going to see what would we need to multiply the a by to get a common denominator. We need to multiply it by the other fraction. So we'd end up with a times x minus 2, and then b times x plus 3. And we need to equate that to the top of the other fraction. And no matter what this top is, it could be a constant, it could be something linear. Keep in mind that it's always going to be something of lesser degree than what we have on the bottom. That's an important part. We'll deal with one that doesn't in a minute. But bottom line is we need to equate that to 2x plus 16. Okay? So from there, we'll do what we did last time. We'll distribute, and we'll get ax minus 2a plus bx plus 3b, and again equals 2x plus 16. We'll collect our x terms here, and we'll go ahead and skip a step here. We'll factor out the x as we do that, and then we're going to add to that, and then we'll have negative 2a plus 3b as our other part. And I put that in parentheses for a purpose, because ultimately we're going to recognize this as the coefficient on x, which means that a plus b, according to our other side, would equal 2, and then our negative 2a plus 3b would equal the constant, which is 16. And then with this system, I would suggest multiplying this one by 2. That way we can eliminate our a's this time. So we'd have 2a, negative 2a is gone. 2b and 3b would make pi b. And then over here on this side, we'd have 2 times 2, that's 4. 4 plus 16 would be 20. And hence this time we'd get b equals 4, value for b. And then if we solve that 4, we would have blank plus 4, a plus 4 equals 2. And we know that we'd subtract that 4 to both sides and we'd get negative 2. Negative 2 plus 4 would equal 2. Alright, so those would be our a and our b values. And again, they're going to go into these two spots. So let's go ahead and put those in there. And so we'd have negative 2 over x plus 3. And remember, we're dealing with an integral at this point still. This is going to be, not 5, but 4 over x minus 2 dx. And of course, we'll separate negative 2 plus 3 dx plus and 4 over x minus 2 dx. We'll factor out the constants, negative 2, and then 1 over x plus 3 dx, and 4, and 1 over x minus 2 dx. And then from there, in both cases, we just have a linear argument on the bottom, which means it's going to be a natural log situation in terms of the antiderivative. So we have negative 2 ln of absolute value of x plus 3 plus 4, natural log of absolute value of x minus 2, plus c. And that would do it. Now, the issue that I discussed a second ago was saying that the degree of the bottom here needs to be bigger than the degree of the top in order for this to work is a fact. The issue is what happens if that's not the case? What if we get a situation where the derivative of, or the, excuse me, that the degree of the top is not bigger, the degree of the top is not smaller than the degree of the bottom, say perhaps x squared minus 6 and x squared minus 9. So what would happen if we had that situation? And the answer is this. Before we can begin with our partial fractions, what we need to do is we need to rewrite this in a different form. So what that means is that we need to take the top fraction, if it's a degree either the same or bigger than the bottom, then we need to actually do the polynomial long division and write it in a different form first. So we know that x squared would go into x once, and if we multiplied it, we'd get x squared, and then minus 9. And then if we subtract that quantity, we'd get nothing in the x squared column, and this column would get a 3. Alright, and we know that we're done dividing here, so our answer, remember, would be 1 plus, and it's the remainder over the divisor. Okay. So that would be our polynomial long division form of the same thing. So remember, this and this are the same function. This is written in essentially improper fraction form, and this is essentially in mixed number form. But either way, they're the same function. If you were to graph either one of these, you'd get the same picture because they are the same function. Now, so if that's the case, then we can go ahead and now integrate. And if we go ahead and integrate, we can separate these two, and we can see that the one part of this is already handled for us. We can see that 1 is just going to be x. So we're good to go there. Now, the question is, how do we deal with this part? Well, now we just said a minute ago that if the degree of the bottom is bigger, we can use our integration by parts technique. Okay? Which means that we can go ahead and do that same technique that we just did a couple times. And if we factor the bottom here, we're going to get x plus 3 and x minus 3. Going to be the two factors of x squared minus 9. We have our a and our b here. And when we do our multiplication, we're going to get a times x minus 3 plus b times x plus 3. And keep in mind we're equating this time with the top with 3. Notice the top is constant, not linear this time, but that's okay. Still going to do the same procedure. So ax and bx, we're going to get negative 3a and plus 3b. And if we factor out a plus b is going to be equal to, and then negative 3a plus 3b is going to be equal to. Now here's the different part about this being nonlinear. Okay, there is no x term over here, so that means the x term's coefficient has to equal 0. There is a constant term, and so that equals 3. And at this point, we would multiply by something to give us a elimination situation. So I'd probably multiply by negative 3. Oops, not 3, doesn't really matter, I guess, in this case, because it's just 0 either way. And so these two would give us negative 6a, and the b's would cancel, and we'd get over here, we'd get simply 3. And so if we divided this time, we'd get a equals negative 1/2. Right? And then if we put our b, if we put our negative 1/2 in here, negative 1/2 plus 1/2 would give us 0. So our system solution would be negative 1/2 and positive 1/2. And so now our sentence is going to read negative 1/2 over x plus 3 dx. And I'll separate it and make it 1/2 over x minus 3 dx. I'm running out of space here, sorry about that. So ultimately, again, we're just filling in our a and our b and our blanks here. And we've already anti-differentiated that part, so that part is just x. In this part, we'd go minus 1/2 out, and the antiderivative of that would be natural log of x plus 3. And the antiderivative of that, of course, would be 1/2 of natural log of x minus 3. And we go plus c, and that's it. Okay. So, with that said, the work would be done. We just ended up with a very similar procedure, but ultimately, before we could begin that procedure, we had to get it into the correct form, which is of the form where the denominator has a higher degree than the numerator. And we could do that same thing if this would have been x cubed or x to the 4th, etc. We would have done exactly the same thing. Nothing would have been different at all about that. Okay, so this there's one more example I want to look at here with integration by parts, and that's the following. We're going to see that we're going to have a differential equation, and it's going to be essentially the same directions here. We're going to have 6x squared minus 8x minus 4 on top this time. And we're going to have x squared minus 4 times x minus 1 on the bottom. All right. And in this case, what we can see here is that we actually have 3 different factors. And when we have 3 factors, then we ultimately need to have them all be linear. So we need to first factor that quadratic factor that we have. Factor it further, I should say. And then, again, now our sentence would read that. So what it boils down to is that whether there's 2 factors or 9 factors, we can still follow that same procedure. And so if we were to set this up properly, we'd have x plus 2, x minus 2, x minus 1, and we'd have still our a, b, and c. Okay, and this time we have a c because we have a third candidate here for our addition. And remember, when we add these two, here's where we have to be careful, because when we add these together, the whole thing is going to be the common denominator. So this one has an x plus 2, but it doesn't have either of these. So we're going to have a times x minus 2 times x minus 1 as our first. And the b is going to get multiplied by these two, which would be x plus 2 and x minus 1. And then the c is going to have to get multiplied by the x plus 2 and the x minus 2. All right? So it makes the algebra a little bit more difficult because we have to do some more multiplying and so on to get our expression. But ultimately, it's just a matter of doing algebra, so we can do our x squared, and this would be minus 3x plus 2 in here. And then our b would be multiplied by x squared, and then we'd have a 2x, and a negative 1x would be plus x minus 2. And then our c here would be multiplied by x squared minus 4. And if we distribute, and we put the terms together next to each other that have the same powered x's here, with it ax squared, bx squared, and cx squared. So ultimately we'd have ax squared plus bx squared plus cx squared. Cx squared, that is. And then we'd have a negative 3xa. And we'd have bx. And there would be no cx term here. So let's go right to the constants here. We'd have a plus 2a. We'd have a minus 2b, and then we'd have a minus 4c.
Mrs. Croft, you have a phone call at 61. Mrs. Croft, L61.
And essentially, we are equating this to the top, which was 6x squared minus 8x minus 4. So, in factoring out our x squareds here, we'd have a plus b plus c is equal to x squared. And in our x terms, we'd have a negative 3a and a b times our x. And then our constant term would be 2a minus 2b minus 4c. So as you can see, like I said, the work is a little bit more tedious here, but it's still the same procedure. Nothing changes here on that at all in terms of the procedure that we use. And ultimately our system then is going to be a plus b plus c equals 6. This is the x squared term we need to equate. We need to equate the 3ab, negative 3a plus b, that is, to negative 8. And then 2a minus 2b minus 4c equals negative 4. Okay. So the other difficulty that we wind up with here in this situation is that we have a solution, we define the solution to a system of 3 equations with 3 unknowns. So in order to do that, remember the technique that we need to use is we need to get this down to a system of 2 equations with 2 unknowns, and then we can do our previous technique. So my suggestion in this case would be to multiply the top one by 2 and then add it to the third one here, because then we'd have 2a and 2a, that would make 4a. We'd have 2b and negative 2b, those would be gone. Okay. Actually, you know what, let's not do that. Scratch that, sorry. Let's multiply instead by 4. Because if we multiplied by 4, we'd get rid of the c's in these two, and then we'd have another equation with a and b in it. That would save us a step. So let's go, we'll go 4a plus 2a, that's going to be 6a. So we got 4a here, 2a here. We got 4b and negative 2b would be plus 2b. And we got 4c and negative 4c, those would be 0. And then over here we'd have 24 and negative 4, that would equal 20 then. Okay. And so with that new equation that we've created, we can now equate that with this one that we wrote earlier. And if we're going to solve this system, I'd probably multiply this by 2. Because if we multiply it by 2, we could get rid of our a's. We'd have 2b and 2b, that would be 4b. And then 2 times negative 8 would be negative 16, and 20 would be 4. And so our b would then equal 1. So we can, again, work our way down to getting one variable, and then we can substitute our way back to get the other 2. So we know that b is 1. That means that negative 3a plus 1 would equal negative 8. And that negative 3a would equal negative 9. A would equal 3, so we got 2 of the 3 so far. We also know that a plus b plus c is equal to 6, and so we know 3 plus 1 plus c is equal to 6, and therefore c would be 2. So with that said, we would know our a, b, and c. And again, the work is more tedious because we have some, number one, we have some quadratic equations that we have to work with in terms of the equating part, and then we also, once we write the system, we have to solve a system of 3 equations with 3 variables. So. But once we have our a, b, and c, then the procedure is no different. We're going to put them back into our original here, a, b, and c, integrate both parts, and without even writing anything down, I can see that the answer, of course, with a of 3 here is going to be 3 natural log of absolute value of x plus 2 plus 1 natural log of absolute value of x minus 2 plus 2 natural log of x minus 1's absolute value, and then ultimately plus c at the end, and that would be our final answer to that one. Okay. So that is the overview of the technique of partial fractions. When we integrate using partial fractions. Part of your homework assignment, you're just going to be working with doing this part, just getting the partial fractions separated, and the other part you're going to actually have to do the anti-differentiation or work with a differential equation as such. Okay, enjoy.